In this episode, we are joined again by Manuel, who's back to present part 2 of his robotics project. In part 1, Manuel showcased a powerful simulation setup using Boston Dynamics bot robot in ISAC combined with ROS2 and a vision language agent. Today, we are taking it into the real world, seeing how the exact same pipeline from perception to action now runs fully on the real robot, performing object detection and autonomous manipulation tasks. We also dive into deeper technical questions from a research group. Thank you all for sending them in.
Hi, we're Bennett and Camilla. We are robotics students passionate about cutting-edge technology, and we're here to explore the newest approaches shaping the future of robotics.
Hey Manuel, thanks again for coming. Happy that you're going to present part 2 of your amazing project today. Could you introduce yourself once again and remind the audience what part 1 was about before we dive into today's topic?
Hey, sure. All right. Hi, I'm Manuel. We did the first video about an ISAC pipeline with a ROS2 perception interface. Why did we do this before this part 2 here right now? The goal was to build a perception pipeline for mobile robots, and before deploying the perception pipeline onto the real robot, we tested all the inference setup, perception results of the VLM. In this case, it was Qwen 2.5 VL. Now showing it in part 2 on the real robot, where we can see how the entire pipeline goes from A to B. We are again using the same agent, the same ROS2 interface. We didn't have to change anything. We just use now the real robot instead of the simulated one from ISAC.
Yeah, I'm still shocked how well everything worked within ISAC. And I'm really excited to see how it will work in real right now. So if you don't mind, could you show us maybe a quick demo, maybe something similar to what we see in the simulation before?
Yes, sure. So what we can see right now is, again, the N8N agent interface we saw during part 1 of this video series. We can do, again, things like talking to the robot. So this is now the real robot, which is called Timon. We can ask now the robot, or we can ask the agent what's the power state of Timon. So this is now a real robot. We're gonna see, okay, the motors are off. It's currently charging. It has about 99% battery percentage, and it has about an estimated runtime of 1 hour and 33 minutes. So good to go that we are now doing some easy manipulation tasks in this case. So we can do now, for example, at first, the robot is now on its docking station. So we can do things like, please undock the robot, while the agent is processing all the requests and pushing it forward to the ROS2 web interface. We can see here right now that the robot has been successfully undocked. In the next step, we can do things like, which could be pretty interesting for this video and also to show the entire perception pipeline. Could be, for example, picking up objects like what we see here on the right, which are gloves which are put on the floor for the robot to pick it up. So what we did before in simulation with ISAC, asking the agent, is there any tripping hazard? And it responded, okay, there is a banana on the floor. We would do now exactly the same with just asking it, okay, do you see any hazards? Do you see any gloves on the floor or whatever? And the exactly same pipeline will give us the result of the object and the object's location in 2D. And we can use then this information to issue grasping commands for the robot, for example. So let us do, for example, please grasp the glove on the floor with Timon. We can see now the agent is processing this information. It asks me now if everything is available, all right, and it's just asking me, okay, if it should go on with it. Okay, go on. It will start getting all the robot's camera's feed get the camera data via ROS2 and the web interface. It will use the camera information and data, push it into Qwen 2.5 VL to get, for example, the location of the gloves here. We have to wait here a bit because it's everything going over a cellular network. All right, so we asked now the agent to get all the camera data from the robot's base cameras, which are 6 in this case, front left, front right, left, right, back, and also the hand image. And we can see now, okay, it got the information, where is the robot going, and where is where is the object's location. And we got here right now, okay, it found the gloves on the floor. We got 2D information from Qwen 2.5. We used the camera intrinsics of the robot's base cameras, and this 2D information we converted into 3D space. And then we used, in this case, the robot's manipulation API and inverse kinematic solver to pick up the object in the real world. So this is what happened here. Gloves have been detected on the floor and successfully grasped by Timon. So we saw now the robot picking up anything. So like a glove on the floor, we can also open now the robot's gripper. So the object can fall out again. So please open Timon's gripper. We can wait now for a few seconds here, and we saw the gloves falling out again of the manipulator of the robot itself. And now we can do exactly the same right now. So we can do again, for example, please grasp the gloves on the floor with Timon, just to see it again for everyone. So the robot is again using all the camera data from the robot's base cameras, asking again the VLM where are the gloves or where is any tripping hazard, and the VLM will give us 2D information about the object's location, and then we are converting all the information into 3D to issue grasping commands with the robot. So it takes some time because we're having 6 cameras on the robot, and it's a Qwen 2.5 VL 32B model deployed on an NVIDIA Jetson Orin AGX, so pretty powerful model on a edge device. So this is pretty cool. And now we can see again, okay, it got the information from any of those cameras and is issuing the grasping command here.
And just to be clear, like all the movements are not done by you. It also like by the model, while you're also able to move it yourself manually, right?
Yes, exactly. So I can move the robot myself here right now, but everything was done now by the implementation we did here. So it's actually done by the API which I built for this agent. So this API is controlling the robot's base movements, but also the robot's arm movements. And I'm using here Boston Dynamics Spot Manipulation API, which is working really well for such use cases. And with that, I was able to do like those generic pick and place or manipulation tasks.
Awesome.
So we saw that the robot now just successfully grasped the gloves from the floor, and it's already asking me, okay, what would you like to do next? And we can, for example, store the gloves maybe in this white storage box here. So we are telling the robot, walk to the white storage box on the floor. So it's again taking camera information, feeding it into the VLM to get the object's location. Takes some time. And we saw now, okay, it approached the white storage box here. There's already a tennis ball in it because I did some testing before. And the next step would be, for example, placing these gloves we already grasped into the box, and it's doing it completely automatically. So I just told it where's the goal location of the object we grasped before, and the agent did everything by its own. So it just asked me, okay, can I go on with it? And I just told it, yes, go on, do it. And then it did everything completely autonomously. So Timon successfully walked to the white storage box and placed the gloves in there. Let me know if you want to do anything else. We're now finished. We can now tell the robot to dock again. Please dock it to 529. So we're finished with this manipulation task, and everything here can be fully autonomous.
It's so incredible, everything. It's mind-blowing. Wow. Now we're going to cover some questions from the research group.
We've noticed you've worked with several vision language models. Recently it was Qwen, but earlier you also were using versions that were called RoboPoint, which we found out is more like an integrated vision language model with some sort of manipulation tasks. And our question was kind of what influenced your choice of models over something maybe even more general like GPT-4 Vision for this kind of perception to action workflow, especially regarding manipulation tasks?
So regarding the questions, why did I choose models like RoboPoint or Qwen 2.5 for my perception to action workflows? The answer is I used RoboPoint and Qwen 2.5 VL because both models are able to do object point or bounding box predictions. So both models are able to give you 2D information about any object on the image. So like we saw before, please grasp the gloves from the floor. RoboPoint and both Qwen 2.5 are able to tell you, okay, the object is on X1, X2, Y1, and Y2, for example. And GPT-4 Vision isn't able to do that, and that's why I opted for those two models. And actually the second, also pretty important information is that both models, RoboPoint and Qwen 2.5, you're able to deploy them locally on your own machines. So when you're thinking about any production use case in any industrial facility, for example, maybe you don't have internet connection where you can query any APIs on the internet. And moreover, maybe you do not want to give any information about the facility like images to any API. So that's why I went for models like RoboPoint and Qwen 2.5 because I'm also able to deploy them locally on my Jetson devices.
Okay, great. And these bounding boxes that you talked about, they help with the 3D perception task for, I guess, post-estimation, right?
Exactly. So to build any perception pipeline, you need information about the environment, about the environment from the robot. So in order to be able to tell the robot, hey, please pick up any object, you have to know where is the object. So that's why you need, for example, 2D information from the VLM or from the model or from a CNN also. You need 2D information, where is the object, and then you can use this 2D information with your camera intrinsics to convert it into 3D space. And with this information, you can use then, for example, IK solvers like MoveIt or vendor-dependent IK solvers to do the actual grasping or motion planning.
Another thing we noticed is that the Scar robot always seems to grasp along what it looks like its neck axis. How do you constrain or guide the grasp sampler to consistently produce those aligned orientations? Is there some stability logic or motion prior to prevent a full body rotation?
So regarding the robot's grasping orientation, this is actually done by the robot's manipulation API solvers. So everything, how the robot is approaching the target is done by the robot's solver. So I didn't have to do anything like, okay, rotate the robot by 90 degrees and then do the grasping. I mean, I could do it, but for Spot, it makes sense that the robot is grasping along its neck axis because it's in front of the robot. So the robot sees, for example, okay, what's in front of him, and then it's doing the grasping task. So in this case, I didn't have to add any logic or motion prior the actual grasping approach. So in this case, everything was done by the manipulation API of the robot.
On our path to research, I feel like a lot of students will encounter this problem too. We were heavily focusing on the manipulation task and wondering which one specifically, which modules SCAR uses in the proposed setup. Is it like based on Isaac manipulator library or like the PIC pipeline that they propose on their website, or do you maybe have something custom? As I said, like the RoboPoint model, for instance, had an integrated manipulating network or neural network, let's say that. And also we were wondering if additionally to that, like to the path planning algorithm that basically comes out of it, or like the grasp sample that comes out of it, if when grasping there is any sort of force feedback or estimation involved when lifting or interacting with objects.
All right, so the question, which manipulation module does Spot use in this setup? As explained before, I'm using here the robot's manipulation API. So from Boston Dynamics, there is a SDK which is pretty good manipulation API, so I didn't have to build anything on my own, so I didn't have to use MoveIt or anything else like any Isaac manipulation like Isaac Ross foundation pose or Isaac Ross center pose. But when using other robots which do not have manipulation APIs already out of the box, this could be a very good starting point to do your perception and also manipulation pipelines. And also regarding grasping feedback or force feedback. So in this pipeline I just showed before, there is no force feedback. But it's a very good input, which should be definitely done in a real setup for production. In this case, I just did grasp it, and it's more or less a fire and forget pipeline. But when doing like it in real production use cases, it's definitely necessary to do force feedbacks.
And also regarding the training phase, I think Muammar already asked a similar question, but we also were super interested in if you solely focused on training the locomotion policy or maybe even extended it to some sort of terrain adaptation, or if there are also other train policies for the arm-based manipulation, or maybe like tool use, something like that.
All right, so I trained a locomotion policy or velocity policy for Spot in Isaac Lab, so that I'm able to control the robot in simulation. So I just trained it to be able to validate my perception pipeline, so to be able to drive around the robot in simulation and to see some different objects like bananas or pellets or whatever. I did not have to deploy those locomotion policies like robot space movement policies. I didn't have to deploy them because this is what you already get from Boston Dynamics. So they are having probably the best policies for their own robots. So I didn't have to do this anymore. I really just used it to be able to move the robot around in simulation. And yes, same is for manipulation. I didn't train a policy that lets the robot's manipulator move around. I just used 2D information, converted into 3D information, and then using this 3D information, I used the robot's IK solver to move the arm around. So it's actually not a trained model which operates the arm.
In the last video, you mentioned that you used the Qwen 2.5 visual language model with 32 billion parameters, which is of course a huge model in that you need a Jetson AGX Orin with 46 gigabytes to run it locally. What drove the decision to run it locally rather than using a cloud-based API? Since we, and I think also a lot of other students, are using smaller Jetson versions like an Orin Nano with 8 gigabytes, we have to consider to use an online inference as a practical alternative. Do you have any recommendations maybe for such kind of setup?
All right, so as I explained already in one of my prior answers, why did I use local deployed models for this pipeline? So major use case is in some scenarios like industrial use cases, you sometimes do not have internet, so the robot is offline. So you're not able to transport any data into the internet, into any APIs to get information. So that's the first reason. And the second reason, in some use cases, you do not want to transport or to send any confidential data from the facilities where the robot is operating in to any API in the cloud. So that's why I'm using Jetson Orin AGX for my VLM. So everything is local. The robot doesn't have to send anything into the internet, and there is no internal data of images going to any internet API.
Thank you so much for presenting your project today and the whole pipeline. I think it was very insightful, and of course also for us answering all the questions. So yeah, thank you again very much, and I would like to just know what kind of future tasks you're planning with this pipeline.
Thanks for having me here again. It was super fun showing the manipulation and perception pipeline. I'm super glad that everything worked and I didn't break anything. So it's also very good for me. Regarding future plans, so what I'm trying to do here is an end-to-end touch vibration sensing pipeline. So instead of having the robot picking up any object, the robot should take a vibration sensor with its gripper, look for a pump or a motor in an industrial facility like a power station, and then it should approach the pump or the motor, and then it should deploy the arm onto the machine, carry out a vibration measurement, for example, for 10 or 20 seconds, then put the arm back into its resting position and walk to the next machine. So this is the actual end project which I'm trying to achieve here. And yes, I'm already very excited doing more progress on these topics.
Yeah, we wish you a lot of luck and a lot of fun with this project, and I'm sure it will be great. So yeah, if anyone in the audience has some questions or wants us to maybe try some other things, maybe also regarding i6sim, ISAC Lab, please let us know. And so yeah, thank you again, and have a nice day.